Hey, everybody, and welcome to 8-3, testing a claim about a mean. All right, so testing claims about a population mean with sigma not known. Okay, so this is important. We don't know sigma. And the objective is to use a formal hypothesis test to test a claim about a population mean mu. And then we have the same notation. I just wanted to put it in here. So N is the sample size, X bar is the sample mean, S is the sample standard deviation, and mu sub X bar is the population mean, okay, which is basically the mean of the sample means, right? We learned that in chapter 7, I believe. So testing claims about a population mean with the sigma not known. We have some requirements. Okay, so really important. Requirements are the sample is a simple random sample. Has to be that. And either or both of the conditions are satisfied. Either we know the population is normally distributed or N is greater than 30. And again, we saw that earlier as well. So then we talk about test statistics for testing a claim about a mean. There's a formula there that I wanted to show you, but don't worry about it. We're not going to use it, but I wanted to have it there. It's really similar to what we already saw. So for the p-values, we're going to find p-values. We are going to use StatCrunch. And again, I left this in there because there's a table, and sometimes actually when you click in Pearson on something, you will get that table. I think there's one problem like that. But you have to look at the degrees of freedom. So the degrees of freedom is the sample size minus 1. And again, the critical values will be given with, if you look on one of these t distributions, it will be given in a table. Let me see if I can find one for you guys. Hold on. Okay, so I did find, this is from our textbook, and this is what basically it would look like. So here on the left is degrees of freedom, and then it depends on if we have a one tail or a two tail, and we'll talk about that a little more as well today. And then these are going to be your areas, just as always, okay? So you can see from this table that if I had a sample of 50, and my degrees of freedom would be 49, I don't actually have that value here. So it's not really the best. Since we have StatCrunch, I think it's better just to use StatCrunch, but I did want to show you. Okay, so we can find our p-values and our critical values using our StatCrunch, okay, basically. So we have an example now. So an author obtained times of sleep for randomly selected adult subjects included in the National Health and Nutrition Examination Study. And those times and hours are listed below. So they're right here. Here are the unrounded statistics for this sample, N equals 12. So we have X bar, S. So that's our mean, sample mean, and our sample standard deviation. A common recommendation is that adults should sleep between 7 and 9 hours each night. Use the p-value method with a 0.05 significance level to test the claim that the mean amount of sleep for adults is less than 7 hours. So the first thing we have to do is figure out, do we meet the requirements? What were the requirements? Well, one of them is that it has to be from a random sample. Well, randomly selected adults. We have one of the requirements. The other requirement is going to come from the data. So I already inputted the data here, and it just matches exactly what we have here. And I'm going to go to this graph, QQ plot. I'm going to select var. I am going to add this correlation statistic, and that's it. I'm going to hit compute. And basically, remember, we have to have either n is greater than 30, which I only have a sample of 12, or it's from a normally distributed population. This QQ plot tells us, so this red line, if everything was right on that red line, it would be definitely a normal distributed population. But they're kind of hovering around it, right? And this correlation number, the closer it gets to 1, the better my correlation is with a normally distributed population. So because it's 0.962, we're going to make the assumption that this is a normal curve, okay? So that tells me that I have the requirements are met. Now, the next thing we want to do is find the claim. Okay, so we look through everything and we have a lot of information. So a common recommendation is this. Here we go. To test the claim that the mean amount of sleep for adults is less than 7 hours. So we have these two things. One is called a null hypothesis, and we say H sub 0, and H sub 0 always has equals. So we want to test the claim that the mean amount of sleep for adults is less than 7 hours. So I'm going to say for the null hypothesis, it equals 7. Because the null hypothesis always has to have an equal. And then H1, which is my alternate hypothesis, we're going to say mu is less than 7 hours, because that's the claim, okay? So we have the claim, and we've now set it up. Well, I guess if I do two separately, we found the claim, good. And then we set it up. We found the null hypothesis and the alternative hypothesis. The alternative hypothesis in this example is the claim. Okay. Done. We have our significance level. Our significance level is alpha is equal to 0.05. Okay, so I'll just put a check. Since we are finding the population mean, we use the sample mean and t-statistic. Okay, so we're finding the population mean. Let's go back to our StatCrunch, sorry. And we're going to go to stat, t-stat, one sample with summary, because all my summary is right there, right? I know my sample mean is 6.8. There's a bunch of threes. Standard deviation, sample standard deviation is 1.99240984, and my sample size is 12. Okay. We want to do our hypothesis test for mu, and we said here that H0 is mu equals 7. And then this is H1, sometimes called the alternative, so H sub A, but it's the same as H1. And here we have less than, okay? And basically that's it. I hit compute and I get a bunch of data. So let's figure out what all this means, okay? So since we are finding the population mean, we use the state. Here, let's go back here. Sorry. So we're using the sample mean and t-statistic, which is also called the test statistic. So that's right here. And there's my p-value. Okay, use StatCrunch. We did that. And then, so we actually did 5, 6, and now we're on 7. So use the p-value to either reject or fail to reject. And what we're rejecting or failing to reject is our null hypothesis. Okay, so let's see. If we have, let me see where I can draw. So let me think, what do I want to do here? Maybe I just want to copy. Hold on, I'll make it nice and then I'm going to pause for a second. All right, so I think this will work. I put my t-statistic and or also called the test statistic, and my p-value right next to each other, okay? And now if I were to look at this, let's just look at it on a straight line. We don't even have to draw our normal curve. So let's draw a normal curve, sorry. Now my p-value is my probability, right? And what that means is that okay, so alpha is 0.05. First thing we need to think about, is this a one-tailed test or a two-tailed test? Well, because of this less than, it's really just a one-tailed test, where this, the probability or the area under this curve right here is 0.05. And then obviously the rest is 1 minus, or 0.95. Now my p-value is 0.4253, which is going to fall somewhere basically in the middle. All the area to the right, I'm sorry, to the left is 0.5. And also to the right is 0.5. Okay, half is to the right, half is to the left. And 0.4253 is really going to be somewhere around here, isn't it? So it is not in my critical region. Basically, this is, if it was in here, I can reject my null hypothesis. Everywhere else, I fail to reject. It's not that I accept, it's that I fail to reject. And I'll describe that in a minute. So for this one, we're going to fail to reject. So if I can't reject, and this, I'm always talking about my null hypothesis. So I really can't reject that the mean value that an adult should sleep in a night. Okay, so we can't reject this, which means really we just don't have enough data. Okay, we can't accept it. We can't, if we fail to reject the null hypothesis, it does not mean we accept it. And if we reject the null hypothesis, then we can go with the alternate hypothesis. But in this case, we can't reject it. Okay, so now let's go through some of these slides and see, because they're going to give us more information. So again, this is the solution. The sample is a simple random sample. I showed you that. And the second requirement is that the population is normally distributed or n is greater than 30. Since the sample size n equals 12, which is not greater than 30, we must determine whether the sample data appears to be from a normally distributed population. And then again, I didn't show you this histogram. This tells me enough information. You can look at both if you like. The accompanying histogram and normal quantile plot, along with the apparent absence of outliers, means there's nothing really way out there, indicate the sample appears to be from a population with a distribution that is approximately normal. So both requirements are satisfied. This was number one from the last slide. Number two, the claim that the mean amount of sleep is less than 7 hours becomes mu is less than 7 hours. Well, that's what we said. I believe this is it. Yeah, mu is less than 7 hours. Step two, the alternative to the original claim is mu is greater than or equal 7 hours. Because the statement mu is less than 7 hours does not contain the condition of equality, it becomes the alternative hypothesis. The null hypothesis is the statement that mu equals 7 hours. So there's our null and our alternative, which is our original claim, and we already saw that. As specified in the statement of the problem, the significance level is alpha equals 0.05. Because the claim is made about the population mean M, the sample statistic most relevant to the sample mean X bar, and we use the T distribution. Okay. So here's what we get. We put all this information in and we get exactly what we said. Because the p-value, oh, they have a different p-value. Must have made a mistake. I should go back. Is 0.389 is greater than the significance level alpha. We fail to reject. We still came up with the fail to reject, but I will go back and see. And the interpretation. Because we fail to reject the null hypothesis, we conclude that there is not sufficient evidence to support the claim that the mean amount of sleep is less than 7 hours. So basically, since we can't reject the null hypothesis H0, because it is greater than that alpha, well, we don't really know what to do. We don't actually have enough information. So we're never actually proving the null hypothesis. We either can reject it and say, well, then it must be the alternative, or we can fail to reject it, which means we actually don't have enough information. That's really our only two choices. Okay, so I did find my error. My p-value is wrong because I typed in 2.99. As we can see, it's 1.99. So if I go back and change this to a 1 and re-hit compute, it goes to 0.3887. I did plug that into the original slides. So it's still, everything else I said is still true. It's just that the value was incorrect. So I apologize for that. So let's continue. So that's where the 0.3887 comes in. And because the p-value of 0.389 rounded to 3 digits is greater than the significance of alpha, which is 0.05, or as I showed you in that picture, well, I can show you again. I can draw that picture again. So if here is 0.05, anything in here is the rejection area. But this value of 0.3887 is going to be somewhere over here. I can't tell you exactly where, but it is in the fail to reject. Okay, so we failed to reject the null hypothesis. Because we failed to reject the null hypothesis, the only conclusion we can make is that we don't have enough evidence to support the claim that the mean amount of adult sleep is less than 7 hours. Just like if I was in court and I didn't have enough evidence to prove someone was guilty, I'm not saying they're innocent. I'm saying that they're not guilty because we don't have enough evidence to prove their guilt. So think of it like that, okay? So now we can do the exact same test, but now this is with a confidence interval method. So let's go back to our StatCrunch and some more. Okay, so if we go back to options, we have all the data here, but now we have a confidence interval. Well, remember, now we're talking about a confidence interval, and the difference between a confidence interval and what we just had was the confidence interval is between two things. So in here, this would be either side of this would be reject. And in the middle is, this is, we believe with some confidence, we believe with, and then some certain amount of confidence, and like we have 90% confidence, 95% confidence, 99% confidence, right? That our mean population is between here and here. That our mu, which is the population, the full population is between there and there. Well, if this is 0.05, then this also has to be 0.05. And now, instead of a 95%, which is what we would have thought we should have, we actually have a confidence interval of 90%. Let's compute. And we get our lower limit is 5.8. Our upper limit is 7.97, basically. So our confidence interval says that mu is between 5.8 hours and 7.87 hours. Well, 7 hours falls in there again. Again, we can't reject that we cannot reject the fact that it's equal to 7 because 7 is in our confidence interval. So either way, we actually get the same information, okay? Move this up. So it's just going to say exactly what I just said. The first example is a left tail test with significant level alpha equals 0.05. So we need a 90% as the confidence level. Okay, remember I just talked about that. So for the given interval of 90%, we got these same two values. And when we testing the claim that mu is less than 7 hours, we use our null hypothesis, mu equals 7 hours, but the assumed value of mu equals 7 hours is contained within the confidence interval. So the confidence interval is telling us that 7 hours could be the value of mu. So we don't have sufficient evidence to reject it. So we fail to reject the null hypothesis, which is exactly what we said and exactly what the other test said as well. So they're going to match. All right, next problem. Is the mean body temperature really 98.6 degrees Fahrenheit? So there is a data set. It's actually in, if you want to go find the data set, it's in Canvas under files, and there's different data sets. It'll be data set 3, body temperatures. And Appendix B includes measured body temperature with these statistics for 12 a.m. on day 2. N equals 106, X bar equal, anyway, I don't have to read that to you, you can read that. So first of all, are the requirements met? Well, we can pretty much make the assumption that they're gonna use a random sample, okay? And also, N is greater than 30, so we've met the requirements. Now we have to find the claim. So what are we claiming? It says use 0.05 significance level to test the common belief, which would be similar to the claim, right? Or exactly the same as the claim, that the population mean is 98.6. So that's our claim. Okay. So now we have to find our null hypothesis and our alternative hypothesis. Well, remember our null hypothesis is always the equal, 98.6. So our alternative, it's not saying less than, it's not saying greater than, it's actually saying that it's not equal to 98.6. This is a two-tailed test. Significance level is alpha is equal to 0.05. So if I was going to look at this on a graph, since it's a two-tailed test, I have half of this, alpha over 2, is in one side, which is 0.025. And also the other half is in here. Alpha over 2 is equal to 0.025. Okay. So we've met the requirements. We found the claim. We found the null and alternative hypothesis. We stated the significance level. Since we are finding the population mean, we use the sample mean and t statistic. This is not, we can't use the z score. We have, because we're using samples, we have to use our t statistic. So we go to StatCrunch, Calc, T-Stat, Summary, which we have this time is summary data. Or if we had the full data, we would go to data. And then we find our p-value. So let's do it. Let's get rid of this. Okay, so we're going to go, just like it says, to stat, t-stat, one sample with summary. And we're going to put our information in. So our sample mean is 98.2. Our sample standard deviation is 0.62. Oh, don't make that mistake that I just made twice. All right, 0.62. Our sample size is 106. We are going to use a hypothesis test where mu is equal to 98.6. 98.6 or not equal to 98.6. And we're going to hit compute. And look at my p-value. Is that p-value smaller than alpha over 2, basically, right? 0.025. Well, it is. So that means if I was going to look at my graph, this is 0.025. This number is way over in here, which is my rejection area. Okay, so now I can reject my null hypothesis, which means that mu, we can reject that mu is equal to 98.6. It is not. Okay. All right, so we can reject the claim, or we can reject the null hypothesis, which means that the mean is not equal to 98.6. So again, let's go through the example. It says requirement check. With the study design used, we can treat the sample as a simple random sample. And the second requirement, that it's normally distributed or n is greater than 30, we have because n equals 106. So we're good. The claim that the population mean is 98.6 becomes mu equals 98.6 when expressed in symbolic form. And the alternative is it's not equal to. So because the statement that mu equals 98.6 is not equal to 98.6, does not contain the condition of equality, it becomes the alternative hypothesis. So the null hypothesis is, so here we have exactly what we said. Now, the last one we did, our original claim was the alternative hypothesis. Here, our claim is the null hypothesis. So as specified in the problem, the significance level is alpha equals 0.05. Since the claim is made about the population mean mu, the sample statistic most relevant to the sample mean, we use the t-distribution because the sample statistic is x bar. So we have x bar and we have everything for a sample, not for population. So we do have what we need for the t-distribution. And I did not calculate this manually. I did calculate this using our StatCrunch. Here is StatCrunch with our hypothesis test. And you can see that the p-value is very small. And here's the same exact thing with our confidence interval. And if you notice 98.6, I'll make it a little bigger, 98.6 is not between my lower limit and my upper limit. So they show the same thing. All three approaches lead to the same conclusion. We're going to reject our null hypothesis. So we're going to reject for the p-value because our p-value is less than the significance level, we can reject it. If we look at critical values, our test statistic is right here, and it's negative 6.64, which falls into the critical region bounded by plus or minus 1.983. That's our critical value. So it's outside of our critical value. If I were to draw a picture, let's see. So our critical values are negative 1.98 and positive 1.98. And if we look at our t-stat, it's way down here, negative 6.6. So it is in the rejection region. So they all say the same thing. Confidence interval The claim value of 98.6 does not fall within the confidence interval, just like I showed you before. So everything that we did worked out perfectly. How do we interpret it? So here we have H0 mu equals 98.6. H1 mu does not equal 98.6. We reject our null hypothesis. So that means that we accept that mu is not equal to 98.6. So there is sufficient evidence to warrant rejection of the common belief that the population mean is 98.6. All right, now, excuse me. Now I want to go through the phrasing of different conclusions. So the concluding statement depends on which hypothesis supports the claim and whether or not we reject the null hypothesis. So remember, we saw two different things, one where the null hypothesis included the claim and one where the null hypothesis, one where the alternative hypothesis contained the claim. So let's read this. If the alternate hypothesis supports the claim and we reject the null hypothesis, we say that the data supports the claim, that whatever it is. If we fail to reject the null hypothesis, we have to say there is not enough data to support the claim. Okay, so that's basically if the claim is in the alternative hypothesis or alternate hypothesis, sorry. If the null hypothesis supports the claim and we reject the null hypothesis, we say there is enough data to justify rejection of the claim. If we fail to reject the null hypothesis, we say there is not enough data to justify rejection of the claim. So if we fail to reject the null hypothesis, we did not prove it was true. Let me highlight that. We merely did not have enough evidence. Oh, spelled wrong. Evidence. Okay. We merely did not have enough evidence to reject it. We never accept the null hypothesis. Again, very important. So let's give a little analogy. So in a trial, the defendant is assumed innocent until proven guilty. So we can say that the null hypothesis, the defendant is innocent. The alternate hypothesis, the defendant is guilty. So the prosecution must provide sufficient evidence to reject the null hypothesis. If this happens, the jury rejects the innocent assumption and returns a verdict of guilty. Otherwise, the jury does not reject the null hypothesis and returns a verdict of not guilty. I should probably read this all over again. Let's start again. If this happens, the jury rejects the innocent assumption and returns a verdict of guilty. Otherwise, the jury does not reject the null hypothesis and returns a verdict of not guilty. The jury does not return a verdict of innocent. Similarly, in hypothesis tests, we never conclude that the null hypothesis is true. So I think that this might help you understand exactly what we're doing in our hypothesis testing. Now we have two different types of errors, obviously. So we have type 1 error. This is the error of rejecting the null hypothesis when it's true. So we go through all of our calculations and we find whatever method we're using, we find that the null hypothesis is we reject the null hypothesis, which means that we say there is enough evidence to prove the alternate hypothesis. However, we could make a mistake, or there can be a mistake. The probability of this type of error is alpha. In this context, alpha is a conditional probability. Then we have a type 2 error. This is the error of not, so let's say I don't reject the null hypothesis when in fact it is false. So I should reject the null hypothesis and I should use the alternate hypothesis, but I don't. I say there's not enough evidence when there is, because we're saying there's an error. The probability of this type of error is denoted beta. And the power, and this is actually the power of a hypothesis test is 1 minus beta. So if you're given the power, then you have to find beta. If you're given beta, you might want to find the power. Just depends on which way it's going. The power gives the probability of rejecting the null hypothesis when it is false. Okay, so if the null hypothesis is false and we reject it, that means we're going to go for the alternate hypothesis. So that is called the power. We will not be doing this. It's just another alternative method used when the population is not normal, which we haven't seen and we're not going to do in this class. And n is not great, n is less than or equal to 30. It's called a bootstrap resampling. It uses the confidence interval method of testing hypotheses, but obtain the confidence interval using bootstrap resampling. So again, don't worry about this. This is not part of the course. It was just something that I wanted to just mention, that there is another way if the population is not normal and n is less than or equal to 30. And last but not least, I have this chart, and I think this will be very helpful. So basically, it's the way you decide whether you're choosing between Z and T. I know that it is hard to decide if you want to use a Z table or if you're going to use a T table. So this is a flow chart that will tell. And let me make this a little bigger. Okay. So we start here. Do we know the population standard deviation? If we do, we go this way. Is the population normally distributed? If it is, we use our z-score. If it's not normally distributed, we find out if n is greater than 30. If it is, we can use our z-score. If it's not, then we use that alternative method that we're not going to talk about. Also, we could go the other way. We don't know the standard deviation of the population. We may only know the standard deviation of the sample. So we go here. Is the population normally distributed? Yes. We use our t-distribution. If we say no, then we go this way. Well, is n greater than 30? If it is, we go back and use our t-distribution. If it's not, we use another method. So I think this really will help you decide between a Z and a T table. And that concludes the actual lecture. I'm going to go now do some example problems. All right, so now we're going to do some problems. I picked a few that I think will maybe help clear up some things that you might not understand. And this is from 8.1, which we didn't go over, but it breaks it down a little bit. So our claim, the mean, so we're talking about mu, pulse rate in beats per minute of adult males is equal to 69.2 beats per minute. So the original claim is mu is equal to 69.2 beats per minute. Check. Okay, good. Identify the null and alternative hypotheses. Well, the null is always the equal, so we don't have to really think too hard about it. It's equal to 69.2. Now, because the claim is that it's equal, then the opposite would be that it's not equal. So we would say mu is not equal to 69.2. If, I have a point there, yeah. So if it said that the mean pulse rate of adult males is greater than 69.2 or less than 69.2, my null hypothesis would still be equal, but the alternative or the alternate would be less than or greater than, depending on which it is. Okay, so I hit check and we go to the next question. So that's basically, let me just go back. So basically, how you want to work through these problems is find the claim. If it's equal, then the alternate is not equal. But if the claim is that it's less than, the null is still the equals, and the alternate is the less than. Hopefully that makes sense. So let's go to question number 2. The test statistic of z equals 1.62 is obtained when testing the claim that p is greater than 0.5. Identify the hypothesis test as being two-tailed, left-tailed, or right-tailed. So my test statistic, which is my z number, and I'm testing the claim that p is greater than 0.5. So basically, let me draw a picture. The probability is the area under the curve. So it is greater than 0.5, so it's right-tailed. Okay, because it would be on, it would be, if this is, this would be, okay, so this would be greater, and this would be less than 0.5. Okay, this is the middle, but in the middle, remember the probability, and that's P, so it has to do with probability. What we're saying is that more than half or less than half. I think that's possibly the best way to say it. So this is a right tail test. Find the p-value. So you can use these two tables, but we could also use StatCrunch. Let's see, I can, oops. Move this down a little. Let me erase that. Okay. So the p-value, we have stat and z equals, okay, so we want a calculator And we want since it's a z-score, we want a normal calculator. And my z number goes in here, 1.62. In here, 1.6, I won't go in there. 1.62. And we want it to be greater than that. And notice that's my p-value. So find my p-value, it's this area under the curve. And we're gonna round to 3 decimal places, 1, 2, 3. That last number is gonna go up to a 3 because the one next to it is a 6. So I'm just gonna copy and paste in here and make this a 3. Using the significance level of alpha equals 0.01, should we reject our null hypothesis, or should we fail to reject? Well, if alpha is equal to 0.01, is this greater than? Basically, what we want to know is 0.053. I'll just put a box, greater than or less than 0.01. Well, we can see that this is definitely bigger than this. That means if I were to draw a picture, and here is my rejection area, and the area here is 0.01, then what I have, 0.53, is going to be in the fail to reject. So I will fail to reject. If I fail to reject, that means that I don't know anything. If I reject, that's good. If I fail to reject, it means I don't have sufficient evidence to support the claim. And that's it. That's really all you want to think about. If you fail to reject, that means that you don't have sufficient evidence to support the claim. Like the last example I did, where we talked about someone being guilty or innocent. Well, we can't really prove someone's innocence, but we can prove that we can say that they're not guilty because we don't have enough evidence to support the fact that they're guilty. So hopefully that clears a little bit up. And we'll go to the next problem. Okay, so now we have an actual problem from 8.3. Park officials make predictions of times to the next eruption of a particular geyser and collect data for the errors in minutes in those predictions. The display from technology available below results from using the prediction error to test the claim. So, okay, here's the claim. Remember, let me highlight it. So we want to test the claim. And the claim is that the mean prediction error is equal to 0. So my claim is that it's equal to 0, but my alternative would be not equal. That's the opposite of equal. If we had the claim was that it's less than a certain value or greater than a certain value, then we would change it, right? Let's see what's in here. I'm not actually sure. Oh, okay. They're giving us all this information. We'll probably use this in a minute. So first thing is we have to say what the null hypothesis is and the alternative hypothesis. Now identify the test statistic. The test statistic is not the critical value. it is this observed value. It's the t-value that you're getting from the information that you're given. We don't have the information, we just have a summary. So here, this would be negative 7.51. Identify the p-value. Well, to 3 decimal places is just 0. 1, 2, 3. That 1 is not going to change anything. So my p-value is 0. So now we have all the information we need, except we need to also know our alpha was 0.05. So state the final conclusion that addresses the original claim. So if our p-value is 0, basically, if we were to draw a picture, and we say that here's my test statistic, minus 7.51, and that goes with p. Well, actually, we don't even need that. All we really need is the p-value. So we want the p-value to be less than the significance level, which obviously it is. So if it is, that means it's here in the rejection area. Okay? If it's in the rejection area, then we can reject the null hypothesis. And we say that, so if we reject H0 here, we say that no, it's not 0 minutes. So let's say it correctly. We reject H0 because the p-value is less than the significance level. There is sufficient evidence to conclude that the mean prediction error is equal to 0 is not correct because we rejected it. There is some error in the mean prediction. If it was equal to 0, then there would be no error. But since it's not equal to 0, there's some error. Okay, so that is that question. Erase. A data set includes data from student evaluations of courses. The summary statistics are, so they're giving us all the summary statistics. We want to use a significance level of 0.05 to test the claim. Here's where I need to look. Test the claim that the population of student course evaluation has a mean equal to 3.75. That means that we have equal as our null and not equal again as our alternative. Determine the test statistic. Well, there's nothing here. We don't have something like we had in the last problem. So we're going to go to StatCrunch. And I think I'm going to put this on one side, put this on one side. And we can move this over. I don't need a graph. Okay, so we have stat. This is, we're given sample information, so we have to use our t-stats. One sample, and I can't get to it, so hold on. Let me put this, sorry about that. Stat, t-stat, one sample with summary. Okay, move it back. Okay, so we just fill it in now. Our mean here is 3.61. Our standard deviation is 0.59. Our sample size is 93. That means we can use it because our sample is big enough, right? Our hypothesis test, we just have to really look here. We don't have to think again. 3.7. Oh, I actually have that number here, 3.75, and not equal to 3.75, and compute. And there's our test statistic right here. And we want to run to 2 places. So that last number is going to be a 9. Try one more time. Oh. Determine the p-value. There's the p-value to 3 decimal places. 1, 2, 3. The number after that is a 4, so I do not round up. Okay, now we have to be careful about this because this is a two-tailed test. So what we want to do is say that since it's a two-tailed test, if the significance level is 0.05, that means 90.95 is here in the middle. And this is fail to reject. But I have these ends here. Here and here. And this is the rejection area. Both of these. Okay. Now, do we reject this? Well, if our alpha is 0.05, that means half of it, alpha over 2, is on this side, and alpha over 2 is on this side. So this is 0.025, and this is 0.025. Now our p-value is 0.024. Is 0.024 greater than or less than 0.025? Well, it's just a teeny tiny bit smaller. So that means it is going to fall in our rejection area. So I'm going to reject the null hypothesis, which is that the mean is 3.75. There is sufficient evidence to conclude that the mean of the population of student course evaluations is equal to 3.75. Well, I rejected it. It's not equal to 3.75. I just rejected it. So is not correct. And there you have it. And then we have another question. I tried to pick some that were a little bit different. It seems like they're kind of similar, but oh well. Now we have data. Listed below are the lead concentrations in micrograms per gram measured in different traditional medicines. Use a 0.10 significance level to test the claim that the mean lead concentration for all medicines is less than, okay, so here we're something different, is less than 17 micrograms per gram. Okay, so we always know our null hypothesis has a 0. has an equal. So we always know that our null hypothesis has the equal. And our alternative is going to have the less than, which is actually our claim. So that looks like the right one. Now we need to download StatCrunch. And let me close this up. And we will put this over here. Over here. Okay, so we go to, now we have, how many, we have 11 things in our sample. Let's see, we know it's a simple random sample. We really should do a graph, QQ plot, to see if it's normally distributed, unless it says somewhere here that it is assumed to be normally distributed. No, it doesn't say it. So let's put our correlation statistic, hit compute. Beautiful. That correlation is very close to 1. Look how close it is on that line. So we can assume this is a normal distribution. So now we can go to stat, tstat, one sample with data. Our data is in bar 1. Our hypothesis test is 17 and less than 17. Compute. And there's our test statistic to 2 decimal places. So I'm going to change that last 1 to a 2. And check. Determine the p-value. It's right here. 2, 3 decimal places. 1, 2, 3. The number after that is a 4. I do not round up. I just leave it alone. Check. Now we have to state our conclusion, and we don't really need our StatCrunch anymore. State the final conclusion that addresses the original claim. So our significance level is 0.10, and our p-value is 0.019. Well, we can see that our p-value is smaller than our alpha. So again, we reject the null hypothesis because it's in the rejection area. So reject H0. There is sufficient evidence to conclude that the mean lead concentrate for all medicines is less than 17. And there you have it. And that's the end. Thanks for watching. If you have any questions, feel free to reach out. And I guess I'll see you in the next lecture.